we've already discussed RF diffusion. This is kind of the next installment of the diffusion series. This is diffusion all atom. Just like RoseTTAFold diffusion was built on RoseTTAFold all atom diffusion was built on RoseTTAFold all atom. The main differences between RoseTTAFold and RoseTTAFold all atom are quite similar to the differences between AlphaFold 2 and AlphaFold 3. The main differences are that instead of just taking in proteins, it takes in other molecules as well. So we have nucleic acids, we have ions, small molecules, as well as covalently modified residues. So it takes in all this information, essentially the sequence of both the protein, nucleic acids, what molecules are there, as well as which residues are modified. Takes all that, throws it through RoseTTAFold 2, essentially. So these are the same exact blocks that we saw in RoseTTAFold, where we had those 3 tracks. We have the single sequence representation, the pair sequence representation, and then the 3D track. They all talk to each other. And then after 36 of those blocks, we go to a final refinement set of blocks that just refine that structural element. And then in the end, we'll have a predicate structure of not just the protein, but also nucleic acids, metals, small molecules, as well as the covalent modifications. This is kind of what it looks like in the way that we transform the raw input sequence data into the features that are used within the network. So sequence-wise, quite similar to what we've discussed before. We just have the amino acid sequence. We search that with some databases to find homologous sequences, as well as homologous templates. So we just search the large sequence databases to find those, and the PDB sequence database to find those structures. For the molecular inputs, which include the small molecules and the covalent modifications, they break it up into the individual atoms. So we have each different atom type based on the elements, as well as we encode the bond geometry, so how the atoms are connected to each other, what kind of bond is connecting them. So for example, the double bond, the single bond, there's also triple and stuff like that. And then they also encode the chiral centers, so we now know what the chirality of the small molecule is. And then each of these different features are the inputs into their respective tracks. So the element type is number of atoms by number of channels. So this is a 1D vector, so we'll go into the 1D track. This is number of atoms by number of atoms by number of channels. So this is a 2D matrix that goes into the 2D track. And the chiral centers is really, it defines like the 3D geometry, even though it is kind of number of atoms, but it still goes into the 3D track because it kind of defines that 3D geometry of the molecule. The 3 tracks I've already kind of mentioned. They include like tension, they include the SE3 transformer, they include the triangle updates, etc. But they all talk to each other and pass information up and down to kind of get all the information from the MSAs, all the information from the templates, all the information from what kind of bond geometries we need for the small molecules and covalent modifications. And they get that into the sequence representation, which goes and makes that final prediction. There's also recycling, and it also predicts the estimated error in its prediction. All right, so that's kind of the overview of what RoseTTAFold All Atom is. Yeah. Yep.
How do they define homology?
So the homology is defined based on sequence identity, essentially.
Okay, so they use a cutoff?
So what they do is essentially just search the database and try to find up to a certain number. So past a certain point, they throw away everything extra. I don't remember exactly what number of sequences they use. It's probably like 256 or 512 or something like that. But it's, yeah, just a bunch of sequences. And the homologous sequences and structures not only work for proteins, but they also work for the RNA as well. They don't include templates and homology for DNA, but for RNA they do include because it's a little trickier to predict. Cool. Okay, so that's what RFdiffusion All Atom is, or RoseTTAFold All Atom, sorry. Let's talk about RoseTTAFold Diffusion All Atom. So just like how they took RoseTTAFold, fine-tuned it for RF diffusion, they did the same thing for RFdiffusion All Atom. So the idea here is we have the given small molecule that we're interested in binding, or we want a protein that can bind the small molecule. We initialize with random noise all around that small molecule, and then we gradually take denoising steps to slowly move more and more towards that predicted ground truth structure. And eventually, we'll get something that looks pretty protein-like, and it has room for the small molecules, some nice looking pockets and interactions that ideally can actually harbor that small molecule. Yeah?
Is there one that works the other way where you can like put a target and then it'll diffuse the small molecule? Is there anyone that does that?
This model does not do that. There are other models that can do that, though. So these are just some of examples that they included in the paper. So they have 4 different small molecules at the top, and then they show 2 designs for each of them where they diffused the protein around it, created a design with ligand MPNN/protein MPNN, and then they refolded it with AlphaFold 2. Remember, AlphaFold 2 can't really predict the small molecule itself, but it still recognizes when there should be room for the small molecule. As we saw, it kind of left room for the metal ions, the other small molecules that were present in the PDB. So it is reassuring that the predicted structures do really match the protein that was generated, and it doesn't really clash with where the small molecule was diffused, or where the small molecule was in the diffusion process. Yeah?
Can the small molecule be placed anywhere and then the protein will be diffused around the small molecule?
So what essentially is happening is the small molecule gets centered at 0, 0, 0, then the noise is generated around it, and then it kind of just diffuses. Okay, let's open it up a little bit. So it's very reminiscent to RFdiffusion, which we've talked about. So RFdiffusion, a little bit of reminder, takes in the masked sequence input. It takes in the previous self-conditioning information, so it made a prediction, and then it's trying to make an update based on that prediction, and then it also has the current set of noised coordinates. Similarly, we have RFdiffusion All-Atom that takes in the masked input, the previous ground truth prediction, the self-conditioning input. We have the current noisy coordinates. We have a fixed small molecule, which is optional, but it's what really allows us to design around that. And then we can also do motif scaffolding. So if you have a specific motif that is maybe interacting with that small molecule, or it doesn't even have to be interacting with the small molecule, it could just be something you want to have in your protein, you can also condition it on that. But then it'll go through RoseTTAFold All Atom, make its prediction of the ground truth. We'll take a step towards that direction, and then we'll keep that process going until we have something that's really nice looking. Like I said, this is kind of what we're doing at every single step. The step process is really the same as RFdiffusion. We make our prediction, throw it through RoseTTAFold All Atom, get our ground truth prediction, interpolate, take a step in that direction. This is now our denoised, slightly denoised coordinates, and we can also use self-conditioning, which they do in inference mode. Questions? These are the losses they used for RoseTTAFold All Atom and RFdiffusion All Atom. Quite similar to pretty much everything we've talked about. Nothing really super new here. We have these FAPE terms that really help make sure that the backbone is where it needs to be, that all the side chains are where they need to be, where all the ligand atoms need to be, where all the nucleic acids and everything need to be. So this is really just kind of just taking FAPE and extending it to these other molecular these other molecules, sorry. And then here we have the 6 degrees of freedom prediction that RoseTTAFold, or TR Rosetta produced. It's those 6 degrees of freedom. There's the distogram, the 2 dihedral angles, and then the regular angle. We have the MSA masked term where we masked portions of the MSA, try to fill it back in to help learn that coevolutionary information. We have our torsion angles, we have our confidences. So these are pretty much the losses that they used for RFdiffusion, or RF All Atom. They trained in multiple phases, increasing the amount of data, increasing some of the crop sizes and some other hyperparameters. And then in phase 3, this is a really fine-tuning stage. They introduce a couple extra terms, mainly for fixing some of the non-ideal geometries that can be produced because we are moving everything around independently. With the frames, with the small molecules, we are also moving the atoms around really. So it can technically produce something that is unphysical, not really makes chemical sense. So they have some terms to really help enforce that, There's also a term for the clashes, make sure everything's not overlapping. And then they also include this extra term L-bind, which is a little interesting. It makes a prediction of whether two chains will interact, which is something that we really haven't seen before in some of these other models, but could be potentially used for discrimination analysis for predicting whether these two proteins are interacting, whether this nucleic acid is interacting with the protein itself. I really haven't seen many people use that or investigate its prediction power. So I think that's something very interesting that could be looked at in the future. But yeah, nonetheless, it's there.
Yeah. You know how they determine the weights of each of the terms?
A lot of the time, it's just kind of arbitrary. They kind of upweight the things that are most important. So in this case, we want to learn to make sure that the structures themselves are most accurate. So you see 10s and 5s. Those are the most heavily weighted terms. We also want to make sure that the side chains are learned really well. The confidences are typically weighted a lot less because we don't want those dominating the signal and the gradients, but they still want to be learned properly. So yeah, that's kind of, yeah, there's not like a science to that, unfortunately. Okay, so that's how they trained RoseTTAFold All Atom. RFdiffusion All Atom is really similar. They use the same loss functions that they used for RFdiffusion. So we have this frame loss to make sure that each frame is denoised. The predicted ground truth structure matches the ground truth structure. So they make sure that the translation vector lines up with the true translation vector for each residue. They also make sure that that rotation matrix lines up with the true rotation matrix for each residue. And then they also do these 2D predictions, which are pretty similar to these 6 degrees of freedom kind of thing. Cool. So that's pretty much all for the main overview of RFdiffusion All Atom. Some limitations. Similar to RFdiffusion, it has hallucinations, loopy regions, elongated regions. Those are just kind of properties of this diffusion process that unfortunately just persist. Some other limitations are that the diffusion part was only trained on protein monomers and small molecules, which is rather unfortunate because RF All Atom modeled covalent modifications, nucleic acids, and things like that. So it is kind of disappointing that it was only trained on small molecules and monomers. It's also only trained on the unconditional task and the motif scaffolding task. So any of these other tasks, the PPI prediction, the fold conditioning, the hotspots, all those are not part of RFdiffusion All Atom currently. So these, I think, are major limitations that really ought to be addressed in the coming years. And I have no doubt that they will be addressed, but this is where we're at currently.
So does that mean it can't predict like the binding of a small molecule?
It can. So what it predicts is, so you give it the small molecule you're interested in, and then it'll generate the protein around it. It won't.
So it can. Okay.
It won't generate the small molecule.
Protein-protein interaction, but it will do protein ligand interaction.
Yes, but anything really past that, it can't do.